For this question, let S be the set of all ordered triple of integers a1, a2, a3 with all of them between 1 and 10. Each ordered triple in S generates a sequence according to the rule an equals to an minus 1 times the absolute value of an minus 2 minus an minus 3 for n or n bigger than 4. Find the number of sequences which an equals to 0. Well, what do we want? An equals to 0, right? This has two choices. One is an minus 1 equals 0. Second is an minus 2 equals to an minus 3. Well, this just goes on forever, right? If none of the a1, a2, a3 equals to 0, this will eventually turn into this. So if any two of the ordered of the a1, a2, a3 is the same, then we will get an equals to 0. Okay, now we go back a bit more. How do we get an minus 2 and the an minus 3 are the same? What does an minus 2 equals to? An minus 2 equals to an minus 3 times an minus 4 minus an minus 5. If these two are the same, then this gives us 1. So we get this, an minus 4 minus, it's not m, it's n. An minus 5 is equals to 1. Now, what we can do is that first calculate how many they are, given that exactly a1, a2, a3, two of them have a difference of 1, 2 consecutive. Okay, so first of all, we have to find how many are possible after being permuted. What does that mean? So first we had to find some way that this works. Then we're gonna permute these numbers. Let's take an example like 2, 3, and 5. Right, this is a possible situation. But how would it be possible? How many choices would there be? Right, 2, 3, 5. Right. How do you permute them into a1, a2, a3? Okay, so two of them has to be consecutive. So it's either gonna be this 5, 2, 3, 5, 3, 2. So there's 4 ways. So we're just gonna multiply whatever we get, multiply by 4. Okay. Now assume two of them are 1 and 2. And then the other one has 7 choices. And the other one's the same. This is the same for 9, 10. We get the other one has 7 choices. Now if the consecutive numbers are 2 and 3 all the way into 8 to 9, like 2 and 3, 3, 4, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9. These, we all have 6 choices. So now, we add them together, we get 224 for this case. For this case, this 4 came from here. We multiply them at the end. Now, we consider the case that both adjacent AS have the increments of 1. So it's going to be 224 plus 2 times 8 plus 2 times 9 equals 258. But we had to note that we have to add the case when you have 3 consecutive numbers in arrangement so that only 2 consecutive numbers have a difference of 1. For example, 1, 3, 2 are a triple, right? But we didn't count, and we counted it multiple times with 1, 2, 3, and something like that. So yeah, 3, 1, 2, 2, 1, 3, and 2, 3, 1. There's 32 more cases. So this gives us 90 cases. Okay, one more thing. If the 2 consecutive numbers in A1, A2, A3 are equal, then this case works, right? It's gonna be like this before, either 2 of the consecutive numbers. So it's just 10 times 10 plus 10 times 10, 10 times 10 plus 10 times 10 minus 10. What's this 10? This 10 is right here because principal inclusion exclusion. The 190. Last one. We generate a pair of A, they have a difference of 1. This can only happen if A3 equals to 1 and A1 equals to A2 plus 2. Or like somewhere around this, right? So we only have 14 choices. So we add them together, we get the answer 494. For this question, there is fx, which is a third degree polynomial, and then there is a bunch of numbers, absolute value equals to 12. And asks us to find the absolute value of f0. Okay, what does a third degree polynomial looks like? Let's not draw the y-axis. We don't need the y-axis. A third degree polynomial looks something like this. It has to look something like this, or something like this, right? Now, if I want 6 of them to be 12, it's gonna be like this. Move it off of it. Well, we know that this is 1, so y-axis is somewhere here. This is 1, 2, 3, 5, 6, 7. Now, after this, we immediately notice that the symmetry line, the line of symmetry, has to be x equals to 4. Because if line of symmetry is anywhere else, it doesn't work. F3 and F5 won't give the same absolute value. So, we know that the line of symmetry is x equal to 4. What we can do now is we move the function left 4 units. Now the line of symmetry is gonna be just the y-axis, and we make things a lot easier because most of them are just negative and positives. Like 1, 2, it's gonna be 3, a bit of out of scale, -1, -2, -3. Okay, so assume this function, we call it fx. No, wait, this is gx, this is fx. Right, assume this gx function. We know that gx is still a third degree polynomial. It's equals to this. We only have 4 unknown variables, so we can just sub in like 4 of the values in there. First of all, d equals to 0. That's a big thing. And then g1 is -12. Oh, and we are assuming that a is more than 0. If a is less than 0, it doesn't really matter, because here's the absolute value. We just need to find d. So yeah, assuming a is more than 0. So g1 is -12, g2 is -12, and then g-1 is gonna be 12. So we write them out. We just ignore the d because it's 0. No. Add up these two. We get 2b is 0, which we get b is 0. So now rewrite these two equations, rewrite 1 and 2. We get something like this. Multiply the first one by 2, and then you minus these two equations. Some regular solving. You get this. And then you write the b and d in. We now know that gx is basically this. Gx is fx moved left 4. Then what is fx? Fx then is gonna be this, right? Yes. So after some calculation, you don't need to like really get it out, but like you can realize that it's just 4 to the power of 3 d equals to f0. What if we just write f0 because we just want f0. It's gonna be 2 times negative 4 to the power of 3 minus 56 plus 56, and we get 72, which is the answer. We get negative 72, but if we take the absolute value, we get 72, which is the answer. For this question, we have an isosceles triangle, and then the in center, and then we have BI, and we want the smallest possible perimeter of ABC. Well, notice that they are positive integer side lengths. This will come in handy later. Positive integer. Okay. Well, let's first draw the triangle. We need it to be isosceles. Something like this. I don't have a ruler here. I don't have a ruler here. Okay, now this is not. This is isosceles, and then we need the incenter. A, B, C, I. We get this is 8. Well, now what we can do is set this to alpha and set this to alpha, because they are this is the angle bisector. AI. This is AI. And then what we can notice is that AI is actually perpendicular to BC because this is an isosceles triangle. And then because these two are the same, these two are going to also be the same. What we can do next is we can just find one side of the triangle. The other side is the same. So assume this is A. We know cosine alpha is A over 8. Now what is cosine 2 alpha in terms of cosine alpha? It's going to be 2 cosine squared alpha minus 1. Then what is cosine 2 alpha? It's going to be this. Cosine 2 alpha is A over AB. Cosine 2 alpha is A squared minus 32 over 32. And then it's going to be A over AB. Cross multiply. Because 32A going to be AB times A squared minus 32. A squared minus 32 has to be bigger than 0, so A is more than 5.5. Additionally, since the triangle IBD, IBD, and then IB is the hypotenuse, so A has to be less than 8. So we can yield A from this. 2A has to be an integer, so A is going to be between 6 and 7. 6 and 7.5. The only possible are 6, 6.5, 7, 7.5. It's not working well. We test them out, and then we get only when A is 6, we get an integral value for all side lengths. The answer, and then we get AB. What's AB? We know AB from earlier, right? AB is gonna be 32A over A squared minus 32. We get the answer is 48. So it's gonna be 48 plus 6 times 2. That's 108, which is the answer. Now this question, consider all 1000 element subsets of the sets 1 to 2015. From each such subject, choose the least element. The arithmetic mean of all these least elements is P over Q, where P over Q are relatively prime. Find P plus Q. First of all, we don't quite understand what the question means. So we're gonna try to simplify, and I'm gonna try to explain to you what the question actually means. Assume there is 1 to 5, and we want to choose the 3 element subsets, and simplify the question to this. So we can list out all the three element subsets. And then they want to choose the smallest one. 1, 2, 3, and then you add them. 6 plus 2 times 2 plus 3 divided by 10. That's the answer we're finding. So how do we do this? Before anything starts, I'm gonna tell you a theorem called the hockey stick identity, which means this. The proof is not hard. You can try it yourself. Now, okay, if you don't know what C means, or you use a different notation, this just means combinatorics, or you use a different symbol, it's fine. So CAB means this or this. No, it's A choose B. It's ACB. People often use all of these 3 notations. Also, the third one wasn't commonly found now. So yeah. Basically. Okay, now we go on to the question. What it's actually addressing is that you have to find the number of 1s, the number of 2s, the number of 3s. We fix one number. The first one. It's 1. We choose 2 from 4. C4 2 times 1. Fix 2. Choose 2 from 3. 2 times 3 C3 2. Choose one number 3. Choose 2 from 2. 3 times 3 times C2 2. Okay. Now we just applied it to 2015 and 1000 elements. Fix 1. Choose 999 from 2014 numbers. Fix 2. Choose 999 from 2013 elements. All the way until fix 1016. Choose 999 elements from 999 elements. And then we add them. We don't do this like normally, right? Because it will be a pain to add them and you won't really know the answer. But we can try this way. We were literally just told, oh, it's right here, this theorem, right? If you take all of these out, these out and replace them with a 1, you can easily get the answer of this is gonna be C 2015 1000, right? Which is the exact number of these subsets, right? Well, what do you see here? Can you take this? The first line just gonna be this. And the second line, we write this. Until the very last line, we write this. So we get 1 of this, 2 of this, 3 of this, however many of this, and we still get the same answer, which makes it way easier. Now this just becomes this. Guess what we can use there again? This function, this theorem. Then we get this. That will be the numerator for our mean. Now what's the denominator? Denominator is gonna be, as you guessed it, C 2015 1000, because there's so many elements. Now this is just simply 2016 over 1001. You can do it with like the definition of C. So you get the answer is this. When you add them, you get 431. Question 13, we have this. The multiplication from 1 to 45 cosecant 2k plus minus 1 squared. Okay, so 2k minus 1, that's all of the odd numbers, and from 1 to 89, and then they want to square them. Okay. What we immediately think is that do it at some cosine I sine way. So assume x is cosine plus I sine 1 degree. Then we get sine 1 is this. And then we multiply by 2 and then take the absolute value. Now cosecant x is going to be 1 over sine x. Right? So let our product m. Then we get 1 over m equals to sine 1 or to sine 179. Because sine 179 is also sine 1, and then we just diverge the 1 to 179 to the other one. It's gonna be equals to this. And then these are the roots of d to the power of 91 plus 1 equals to 0. So we now get equals to z to the power of 90 plus 1. Now we got 1 over m is 1 over 2 to the power of 90 of these things. And we got 1 over 2 to the power of 98. So m is equals to 2 to the power of 89. So we get 91. For this question, we have a function here. Y is less than x and the floor of square root of x. And we're gonna intersect with 1 less than x less than n, which is basically just like 2 lines and everything in between. Now we want the overlapping part to be an integer value. How do we do that? Well, first, why not try to draw out the y is less than x times floor of square root of x. What we get here is like this. That's 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. The graph is gonna look something like this. It increases by a trapezoid. So if 1 less than x is somewhere around here, right? And then somewhere around there, right? We can analyze how much of the trapezoid area it's adding on each for each x. Like this, added this, added this, or this, added this, right? Well, let's see. Let's see how do we do this. It's showing that the graph is compound of trapezoids ranging from h squared to a plus 1 squared on top of the diagonal line y equals to ax. The width of the trapezoid is 3, 5, 7, etc., etc. Whenever a is odd, the value of an increased by an integer plus 1 over 2. Whenever a is even, the value of a increases by an integer value. You can probably see why. You can calculate the smaller ones and then find out. Since each trapezoid always has a odd width, which each value of n is not an integer when n mod 4 is equals to 2, and an integer when n mod 4 is equal to 0. So only when a is divisible by 4 or a is odd is possible. So let's write that out. So every single n in when a is divisible by 4 is possible. So like this. Like that. And then when a is odd, remember you gotta divide it by 2. And then you calculate the bit and then add them together and you get the answer 483. Last problem, a block of wood has the shape of a right circular cylinder with radius 6 and height 8, and then its entire surface has been painted blue. Points A and B are chosen on the edge of one of the circular faces of the cylinder so that AB measures 100 degrees. The block has been sliced in half on one plane that passes point A, point B, and the center, revealing a fat, unpainted face on each half. The area of one of these unpainted faces is a times pi plus b root 3. Now we want to find a plus b plus 3. What do we do here? The face that got cut probably looks like somewhat like this. Which we can't quite calculate because we don't even know if these two arcs are on the same circle. If they are on the same circle, but we can calculate this, and then we can get this. But I don't know if they are the same circle or not, which makes it even harder. Well, what do we do here? If they are not on the same circle, then we might as well make them on the same circle by transforming, or you say projecting. Project this face on a circle. What circle? The bottom circle. Project it on the bottom circle. And you only need to find a ratio, and then you can find what's the area. Note that they are similar, so you can do that. If they're not similar, you can't do that. Well, you can project anything onto a surface, and they will still be similar. Well, now let's try to calculate it, right? So, call the center D, and then this is, I'll call the center O, and then this is gonna be D, C. The projected is gonna be D prime and C prime. Now, make a perpendicular line from O to A, B, C prime, D prime. Connect this to the midpoint of AB, and then connect this. Call this point M. We need to know, call this N. We need to know what is OM divided by MN to realize what is the similarity ratio to find out. What is it then? We know that the height is 8. So we know that ON is going to be 4 because it's half of the height. Now we just need one more to go. How do we do this? What does that mean? It's actually pretty easy. Because AB held a 120 degree angle, we know that OMN is gonna we know that MN is gonna be 3. We know the radius is 6 and it holds a 120 angle, so it's gonna be half of it. So MN is gonna be 3. Then we get OM is 5 because of the Pythagorean theorem. Now we know the similarity ratio, which is 5/3. So we just need to find out whatever a, b, c prime, d prime is, and then multiply it by 5/3. What is a, b, c prime, d prime? Well, let's make a circle. Can't shift here, so it might be like out of scale. Okay, why? And like that. That is the area we're trying to find. And this has 120 degrees. Doesn't look hard. After a bit of calculating, a, b, c prime, d prime, you'll find that the area of a, b, c prime, d prime is 18√3 plus 12 pi. Because you know this is 6, and you know you can calculate it by, I'll use a different pen here to make it clearer. This is 6, and then you know this, it's 1/3 of a circle. You know this because it's a triangle, so you can do it. So we now know what's the a, b, c prime, d prime, and we just gotta multiply it by 5/3. And then the answer is 20 pi plus 30√3, which the answer will be 53. That concludes the entire 2015 AIME1. And then overall, this is not that hard. And yeah.